Good afternoon, everybody. Thanks for coming to this colloquium on this semi-holiday. My name is Anthony Bonfils. I am a postdoc at Nordita, and I have the pleasure to open this colloquium and to introduce the speaker, Professor Alain Gorielli. So, Alain is a professor at the University of Oxford. He obtained his PhD in 1994 from the Université Libre of Brussels. Then he moved to Arizona for a postdoc, and then there he climbed the ladder until professorship. In 2010, he moved to the University of Oxford to take up the inaugural chair of mathematical modeling and to become the director of OCAM, the Oxford Center for Collaborative Applied Mathematics. Since then, he also became the co-director of the International Brain and Mechanics Lab, and he received several rewards and prize for his great work. So he is a fellow of the Royal Society. He has got the David Creighton Medal a few years ago, and he has also written 3 books, one of them being a short introduction to applied mathematics, which I strongly recommend. So he contributed to many aspects of applied mathematics, both practical, like on the new batteries and new photovoltaic cells, on some biology aspect, and also on some more fundamental aspect like foundation of mechanics. And today is our pleasure to hear more about tiling. So the floor is yours, Alain.
Thank you very much, Anthony. It's great to be here. So today I'll talk about tilings, natural tilings. I'll give you an explanation of what I mean by that. It's joint work with a group in Budapest University of Technology Economics, mostly the group of Gabor Domokos, a good friend. We've done a lot of exchange over the years, and he kindly asked me to join for this research project. Ákos Horváth is a professor of mathematics, and Kristina Regos was a PhD student who worked on these things. So the talk today will be based on these 2 papers, the first one in PNAS Nexus in 2024, and the other one we just published, where we just got accepted a couple of weeks ago. So if you look in terms of nature and tiling, you'll find two categories. Hard rock on one side, where the things are mostly linear, and faces as linear and all that. And for that, we have quite a lot of tools to understand tilings and patterns that are made by polyhedra or polygons and all that, going back thousands of years. But you also see in nature things that are more curved, like foam and so on. And where there is quite a bit of work, of course, in physics, essentially going back to Kelvin, as we'll see, for this type of problem, there is no general overview of what tiling you could have with curved faces, curved edges, and so on. And so the goal here is to try to think of them very globally and then find instances in different aspects of science and nature and physics where it is occurred. I will start with planar tiling because it's very easy. Again, if you look around you, you'll find plenty. I'm going to go to the example, but in biology, you have plenty of patterns in art and design, in engineering and so on. At the cellular level or a larger level, you'll find plenty. Here is an example of a tiling. So what is a tiling? Well, it's a covering of space, in this case the plane, it could be full space, with elements which are tiles, or what I call cells actually, without overlap and without gaps. And here is an example. It's an actual mosaic of, sometimes they call mosaic. It's an actual mosaic of, you can find in Alhambra, it's 13th century, in Granada. Beautiful. And you see that I put that in purpose because a mosaic or tiling does not have to be made with pieces that are just polygonal. Here you have curved pieces also. So we make the distinction of tiling that can be tiled with a single cell. In this case, we call that monohedral if the cell is polygonal. And there is a delightful little book by Okusai, the same Okusai from the Great Wave, about design and patterns, where he explores a lot of different ways to tile the plane. And here is an example of a monohedral tiling or monotile. But you can also have pieces that are curved, like monohedric tiling, like the case of the Spectra, which is an aperiodic tiling of the plane with a single piece, a monotile. That was a big discovery, because all these years since the discovery of Penrose, of the Penrose tiling with two elements, it was an open question whether or not you could have aperiodic tiling with a single tile. And that was finally demonstrated in 2024. If you have more than one piece, we'll call this polyhedral tiling if it's made of polygon. And here is Penrose on his own tiling that are the entrance of the University of Oxford Mathematical Institute. So since we're in Sweden, it turns out that Roger got his Nobel Prize right. He was announced in 2019, but he was supposed to come here to give his acceptance lecture in 2020. But by that time we were in lockdown. And so I was asked to take picture of him for the, the nice poster they made and all that. And that's one of the picture I sent for that of Roger Penrose on his Penrose tiling, made of two rhombi, and he specially designed them for the institute with a special little arc, and it has also delightful properties. So these are made with polygonal tiling, but you could also have polyhedric tiling made of curved pieces. And here's an example. Escher has explored that in many instances, all the different ways you can tile, very intuitively, but very beautifully. And here's an example of bird and fish where you have two tiles that tile the plane. Here is another example. That's what we're going to use to build our intuition. This is actually cracks forming in lava. It's not completely solidified yet. And we can, of course, first tendency would be to say, forget about the detail. We can idealize this structure as a covering of the plane with different cells. And so when you look at a tiling, there are two important quantities that are really dual to each other. There is the cell itself, one unit, one tile, and there is the node where you have two edges at least meeting, right? And what you want to do is assign numbers to both nodes and cell in order to see how patterns fit together or different patterns organize. Okay, so in terms of cells, an important distinction is whether or not a cell is convex, so that if you take any 2 points, the line between the two is also inside the cell, or is non-convex, where you can find 2 points for which the line is not in there. It turns out that convex cell is an important condition you can prove a lot mathematically, and much harder to classify and understand tiling made with non-convex cell. So let's assign number. For one cell, you can count the nodes on the boundary. So the nodes, if you have 2 or more edges that meet. And for a given cell, you count the node. In this case, you have 5 different nodes. But we make an important distinction, and you'll see why in a second, is that there are times where the number of nodes doesn't match the number of sides of the cell. So for instance, in this case, I have a T junction, right? So I have 4 sides, but I have 5 nodes, okay? So this number I will call the corners, because if I'm inside the cell, this is what I see. I don't know that there is an edge going T, because all I see is the inside of the cell. I only see 4 corners. Okay, so this one I call V star. In this case, it would be 4. Okay, so we assign a number to a cell. We can now assign a number to a node. And the number to a node is going to be, the first one is going to be the number of cells that are around that node, how many cells come in. In this case, it would be 5, or the number of corners at that node. In which case, it would be 4. Okay, so we have a definition. Let's make sure we understand. Back to the same tiling, we have a regular node. We have N. We have 3 edges coming there, 3 cells around. That's a regular node. But this one is irregular. So we have 3 cells around that node, but we only have 2 corners. Right? There are only 2 corners in that little circle there. And if I look at this cell, it will have 6 nodes around it, but only 5 corners. Okay, and now I can average that. I can take a point and assume that the position of the point does not matter, meaning the average that I'm going to compute is independent of that point. This is the class of tiling we look at. And I count in a radius r these different average t's on a radius r, right? And then I take the limit to r going to infinity, which gives me the average number of side and the average number of degree at each node. So that gives me 2 numbers, v bar star and bar star, for the entire tile. And now I have 2 quantities that classify the properties of the cell, on average how many sides I have, and the properties of the nodes, on average how many nodes come around it. And a third number is to count the number of regular nodes proportionally to the total number of nodes. So in this case, in this circle, I have 11 regular nodes and 4 irregular. So I have 11 divided by 15, and I take the limit r going to infinity, and that also gives me a number. So I have 3 numbers now for any given tiling in the plane. Okay, so let's do a little bit more of warming up. A square lattice, 4 sides, 4 edge meets. It's the simplest one, as you expect. N equals 4, V equals 4. All nodes are regular, and you find plenty of examples. And the early example in terms of cellular material, you can find that, for instance, in Hooke's Micrographia, published in 1665. This is quite a remarkable book. First, it's really big. It also was the first international scientific bestseller ever. He opened the world to a new world that nobody has ever seen before, microscopic world, right? And if you see the cork, that's this typical structure of cell. He also coined the word cell to describe this type of structure, and all biology the word cell in biology comes from that. Here is a hexagonal lattice, 6 edges. We have 3 edges meeting at each node, and all nodes are regular. There is no T-junction. Again, you see plenty of examples of that. And you see that there is a trade-off between the number of edges and the degree. If you have more edges, you cannot fit them together. And this is the type of constraint that we have. I don't know why I have that twice. Okay. So now we can try to order that, see the trade-off between the degree and the number of edges. And we can organize that in that plane. N versus V, V star the number of corner, and the degree, and star the average degree. And the trade-off is very simple. In case of regular convex tiling, you can have 4, 4, square lattice. You can have 3, 6 for hexagonal lattice. Or you could have 6, 3, the dual. It's really the dual between the two. It's 6 and 3 for the triangular lattice. And anything in between is on this hyperbola here, right? So here are 2 examples, for instance. So any kind of regular tiling sits in that plane in there. We also call it the Schläfli plane. Schläfli was a mathematician from the 19th century, Ludwig Schläfli, who worked on classification and polytope and described the same type of number. His work was actually completely ignored until late in the 20th century. So another example, I think very nice, is what we call primitive tiling. Now you can think about random tiling. So for instance, when you have cracks, the crack propagates toward the entire structure, right? So you have all this line crisscrossing. And a primitive tiling, the ideal model, is that tiling made of random lines in the plane, right? So I can take a bunch of random lines. And for these random lines, it's easy to convince yourself that with probability 1, you'll have this type of intersection between 2 lines, right? And with probability 0, or on average 0, you'll have no intersection where 3 line crosses, because that's very unlikely, right? And so since the degree there, it's always regular, and the degree at a node is 4, directly we know from from that theorem, very simply, that the average number of sides must be also 4, right? You just plug it. And so random primitive tilings are all there. What else do we have? Well, we recognize the one that you love and maybe have played with. You have the random tiling. You have the Voronoi tiling right there, and they're on average 6. They're random, but they have that structure by the way they're being built. And you have the dual, which is the random Delaunay triangulation. Right? When you triangulate a surface, it's really the dual of the Voronoi. And so now we have a good understanding of that. We can see how they fit. That's nice. What about irregular tilings? Well, in an irregular tilings, here is an example. And this one is completely irregular. All the nodes are actually the same. And you see that you have red square and yellow square. And wherever there is a node, there is a T-junction. So there are 3 edges, but at each edges, in that little circle, you only have 2 corners. Okay, so n star equals 2. And again, for very good reason, you see plenty of example that for cells or brick, because you don't want to have lines of weakness, you juxtapose them, right? So that's a typical feature of that. You can play the same trick and count the possibilities and make sure that the angles fit and all that, and you get to the result that all these also fit on a hyperbola a little bit below in the same plane. And that's very small hyperbola there. You have all the possible solution of this type of tiling. Now, what for tilings that are partially regular or irregular, anything between 0 and 1, well, they all sit in there. All convex polygonal tilings are right here. Right? So now you have in that plane, you know where they are. And again, it's very nice because there are plenty of examples in nature of that. You can look in nature. This was done by Gabor Domokos's group, where they went around and measured different things and picture of cracks and leaves and other type of structure. And they all sit somewhere in there, right? So you have a good understanding of the different type of structure. And this is where really we start our conversation today about soft structure. What's out there? Well, we know that they are non-convex tiling. They're also hyperbolic tilings. So we know that there are things there. But the real question that we have is that, okay, it's easy to prove that polygonal tiling can have at minimum 3 sides, right? Because you can't have 2 sides in a polygon. But can you have tilings with fewer corners, right? So is there something here? And if that's something, how do you describe it, how you build it, and so on? So back to 1824, back to Okusai. Let's look at this picture, and let's talk about what we call soft tiling, the concept of soft tiling. So if I look at this picture, it's easy to extend it to infinity and convince yourself that with a few pieces, it actually fills completely. So it is a case of polyhedric tiling, and if you zoom, what you'll have is that each piece looks like a little crescent like that, and that crescent is non-convex, of course, otherwise it would be up there, but it has only 2 corners, right? There are only 2 corners at each of these pieces. So it's a soft polyhedric tiling. Can you tile the plane with a soft structure that with a monotile? Well, this time we go back to Robert Hooke, and this is a drawing of seaweed. And if you forget the little bob, you realize that the unit cell here can tile the entire plane by repetition, right? And this is what we call a soft cell. So we call a soft tiling or soft cell when it has the minimum number of corners. And in the plane, that minimum number is 2, and it looks like that. Well, if you make it a little bit straighter, the flexible, you can move it a little bit, and there will be just a little unit like that you repeat. More generally, you can start with a tiling that you know, for instance, the square lattice, and say, I'm going to deform it to soften it. I'm going to remove corner in the process, right? So if I make the top edge half a circle, and the bottom edge also a half a circle. Now I eliminate two corners because the tangent now align, so I don't have a corner there. And I have two corners and two edges, and then I can pile them together. Here is a different example. If you like wine, you go to a wine shop and buy an expensive bottle, and the expensive bottle comes with a wrapping, and you bring it home, you throw away the wine, and you keep the wrapping, and the wrapping would look like these little cells that are repeated, right? So that's another example of soft cell. And if I look at one node, I see that there are two corners in each node, right? Each cell has two corners, and each node has two cells at two corners in that little circle. Right? So it's a soft cell, but a different one, and it's what it looks like. So the result now is that on this plane, we have two examples here, and the theorem is that the minimum number that you can have for this type of geometry fully in 2 dimensions is 2. Right? So this is the minimum that you can do. And if you have a given tiling, you can always soften it by doing this change of angle for the edges. So we do what we call edge bending and align them, but you have to do the same at all places, at all nodes at the same time. So the edge bending, you take, for instance, a lattice like that, and you can align different half tangent at a node. So if I do it at 1, it will look like this one. And I repeat that, the same operation at all the nodes at the top. And then I do the same at the bottom, and I soften it my tile, right? So I obtain a structure like that. So now you can start with the 3 possible monotile with regular polygons, and they're only the one for the hexagonal lattice, the triangular lattice, and the square, and soften them and classify them. And here is a full classification of all the different cases that you have. So there are 12 possible ways to have soft cell in 2 dimensions. And you go around and right away you start seeing a lot of application, either in the shape of stream, in landscape, in the shape of bacteria, fungi, the shape that a blood cell take in capillaries when you have a high flow. It's another example, epithelial tissue, little corner of ear, but also in architecture. For instance, Zaha Hadid, the so-called queen of curves, had a lot of buildings that are made of shape that she tries to very obviously, intuitively, to remove corners to give them more organic shapes. So you see a lot of that. And here is another beautiful example that you find in art, which is Escher, that again has studied all possible type of tiling. And you see that these 2 different fish together actually made one of these soft tiling. So when we realize that, we see it looks like we find a lot of them, actually, and maybe they're somewhat generic. So how we would go about doing that? Here is a start. We are just starting to think about how to do that properly. But suppose that I take n disk in the plane, in a circle, and I let them grow until they touch each other and cannot move anymore, right? So I let them move, they grow up until they reach this point. And now I count how many corners each cell has, where I count also as cells the white space as a one possible cell, right? So this is what it looks like. And if I look at the numbers, well, if I can look now at each cell and count the number of corners, and you see when two circles touch, they touch tangentially, so they don't have any corners there. This is just the other 2 that matters. So the circle have no corners, obviously. So if I do the count, I have 10 plus 12 in this case, plus the outside that I can consider as a giant cell. So that's 23 cells, and so that's a total of 42 corners. And the average number of edge is then average number of corners, 42 divided by 23, which is less than 2, because the geometry is not the one of a plane. And that's also something you can derive. So generically, if you start letting cells grow and interact, if they can deform, they will get to that number. And that's what is interesting, because we know that they can deform, but without adhesion, if you have two cells growing, they might deform elastically, and they would still be soft cell, right? If you count now, these are still soft cells, because on average, it's still each cell has only two corners. And it's only if you start adding more physics, if you start adhesion or surface tension or other process, that you're going to start hardening this soft cell. The soft cell are the generic one, and as it grows and the tissue in biology, etc., start interacting, you have to add more physics in order to change the number or harden the tissue, if you want. In this case, you would have more a hard tissue. And so it's an idea that people had a while back in terms of morphogenesis, that very early on cells, the way they are arranged, are very soft, and it's only later on in development that they really start looking like polygonal tessellation, right? But in order to do that, what you learn is that if you really want to have a polygonal tessellation, like in an epithelial cell, what you need is specialized protein. So you need more information, more physics, something that at the intersection would take the three cells that meet at one point and bring them together and glue them together at the tricellular junction. And so you have specialized protein in order to do that. The generic case is soft, and if you want to get to the hard one, it's really a limit process in which you have to bring the different cells together. And so Honda, for instance, in the 80s, had these ideas of tissue starting in a way soft and evolving to a strong structure, harder structure as it goes along. Okay, so that's good. What about, we have that understanding for 2D, but 2D is easy. And 3D is more fun and more interesting. So the first thing we know about 3D hard polyhedra is that, unlike the plane where every number past 2 is give rise to a regular polygon, a triangle and so on, for any n, n-gon, in space you can only have, to satisfy the condition on the angle, you can only have 5 different polyhedra. And this is known by Plato, so that was called Plato's polyhedra. And Plato thought about that as the 5 different elements that makes everything. So earth, water, fire, the universe, and so on. It's attributed to each of them. For instance, earth was made of cube. So he thought of them, so like the proto-idea of atoms, really, in order to do that. And if you take him completely seriously, and he thought about that as packing, that these different constituent or these different polyhedra would be a packing unit, it turns out that he was wrong. Of course, that's a very extremist way of looking at this. But if you think whether or not these could tile space, the answer was wrong. And Aristotle already proved that. He showed, no, you can't go around and tile space with octahedron. It just doesn't work. And according to Aristotle, you could only have the cube and the regular tetrahedron. So what are the numbers associated with that? So the number associated with that is that if I take a cube, so I got that from Nordita's game room. It's from your university, Stockholm. It's called the 8th dimension of academic teachership. I don't know what the 8 dimensions are, but there are 8 cubes. So if I take a node right here, right, and you see that there are 8 cubes around that node. They're the 8 cube of academic leadership or teachership or whatever ship. Okay, so that n equals 8. So what about regular tetrahedra? You see right away, so, how many tetrahedra can I block around? What is the node? So let's do a little auction game. You win if you get the right number, but you lose if that number is too high. So who wants to guess how many regular tetrahedra you can pack around to fill? We're going to do like like with students, where I'm going to wait until somebody cracks and gives an answer. You know the trick when students refuse. Hmm? Yes, it's right there. Wait and see. You're not going to win the auction if you don't say anything, and you have nothing to lose because you don't pay money. You put money on it. So, who wants to venture a number? 12. Excellent. That's a good start. We have a winner here already. So, unless somebody says more, maybe. 16. Very good. Any higher number? You have nothing to lose. 24 is not bad. Yeah. 24 is very good. 18. Yeah. So you see, I mean, the point here is that it's actually very hard to picture things in 3D, even with a regular tetrahedra. And the number is 22.79. Because, well, 24 was the natural one. That's the one I guess also at the time. Well, if you think about how to put them, but it's actually 22.79 because the regular tetrahedra does not tile space either, right? It's if you look at the angle, the solid angle and all that, and do the count, it just doesn't work. It either leaves a little opening or it overlaps if you add one or two. But 24 is certainly the best guess. There are plenty of ways of tiling space with non-regular tetrahedra. So, but in terms of regular surface, the one that you can salvage is actually the truncated octahedron, and that's an example of Archimedean's polyhedra. So here I take the regular octahedron and I truncate and I replace the little pyramid by squares, right? So that's a very nice little unit now that I have. And it was shown by Fedorov in the 19th century, but also studied by Kelvin, that T is a tiling unit for space. It's actually the only Archimedean's polyhedra that can tile space. The Archimedean polyhedra are made with regular polygon and being transitive, that each node is the same up to a symmetry. But the other one that we know are the parallelohedra tilings, and there are 5 of them. And these are all the shape that tile space by parallel translation in 3 directions. Right? So you can't rotate them, but these are the five known. And that's, again, something that Fedorov proved in 1885. So now the question that we have is that can we play the same game? Can you soften these cells? Are we ready for another round? Round 2? Okay. So remember that we went from 4 corners to 4 edges to 2 corners and 2 edges, right? And so now, if I take the cube, can I soften it in some way to reduce the number of corners? Okay, so the cube, remember, 8 corners, 12 edges, 6 faces. How low can I go? What is the minimum that I can do? How can I soften it? Right? Now, the rule is I can bend the edge and move the faces and so on. And so now the game goes the other way. If you go too low, you lose the game. And if you get the right number, you win the auction. So let's open the auction. I have 4. Somebody wants to go lower than 4? 2 is winning now. Anybody wants to go? 1? Yeah, 1 corner. Did I hear 0? Did I 0 on my side? Yes. Well, the answer, my friend, is 0. You can soften, you can always eliminate, well, not always, you'll see in a second, eliminate all corners. And I'm sure you want a proof of that. So it's not a 1-line proof. It's a 0-line proof. It's this shape. And it's this shape that I have here. It has proven 2 images. The first one is a movie. It shows teeth. And if I follow, you can come after and you play with it. Follow the edge. There is only 1 edge, 2 faces, and 0 corners. 0 corner. Right? And the second part of the proof is that it tiles space, because if I take 2 of these, you realize that they are compatible with each other. And then I can put as many as I want in a line, and I make a prism, and that prism has a square square cross-section, and then I can pile as many of these prisms as I want in the other direction. Okay? So how do we get to this shape? That's interesting. Now this shape exists. That's an existence. Now we want a constructive way to look at them. I start again with the square lattice. I identify one node, and what I need to do is to bend the edges, but I have to keep track of the edge. So here is how it goes. I start bending the edge on one side, I do it on the other side, and now that I have done that at one node, I have to do the same at all the other nodes. Right? And then when I have that, I have again a lot of flexibility. I can isolate this one cell and deform it so that it keeps the same rule. Of course, there is an entire family of these. And they're all aligned like that. So there is an entire family of these because you have a lot of choice that you can do as a function between the two. So the way we build them to make them mathematically more interesting, there are plenty of choice, you can make variation of that, is that the edge is made of a Dubin's path. If I give two tangents in the plane, Dubin's path is the one that is the smooth curve that has the shortest length between the two and match the two tangent, and you can show it's very important in control theory. Usually you put a lower bound on the curvature, so you can show that it's made of straight line and a piece of circle. That the solution of this type of problem. It's also very important for a train track. If you play with train track, train can only turn a certain amount, so they have a limit on the curvature. So if I have a train that has to go from here to here in the plane, the two tangent, I want to be able to build a track that respects this condition on the curvature, but also has the shortest overall length. So I have this length, yes? So you do have discontinuity, but the discontinuity arises at the edges, right? When two faces meet, that's where you have a discontinuity. And a corner is defined as a node is defined a place where there is no smooth curve going through that belong to the boundary, right? And so for the face themselves, we take the edges as boundary, and we build the minimal surfaces out of these edges. Right. So that's just for construction. Again, these polyhedra is very aristocrat family of shape. You have the king and you have a few dominant one, the 5-1 and the cube, blah, 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 and nothing else. The rest do not exist. Whereas the soft celled equivalent is much more of democracy, where you have a lot of possibility, all doing things slightly differently. So what about other shapes? When you understand that edge bending theorem, you can say whether or not you can apply it to other type. Can you start with any given lattice that you know? It doesn't have to be built on a single one. It could be built on as many as you want. And deform it to create a softer version of it. And the theorem that we had was that if you start with a convex polyhedral tiling, we have certain condition to show that you can always soften it. And the condition is quite nice, the way we formulate it. The problem is to keep track of all the tangent coming in and make sure that the same happened at every node, right? So you have a combinatorial problem of connection, and you can rewrite that as a graph problem. And the answer, the technical condition that we have, is that if you look at one node, you put a sphere around the node, and the intersection of the sphere with the edges give you intersection point, and you build a polyhedron around that. So for instance, in the case of the cube, what you build is a octahedron. And once you build the octahedron, you take the dual of the octahedron, which is the cube, and the condition is whether or not you can find a Miltonian circuit on that polyhedron And if you can, then you can always soften it. So what is a Hamiltonian circuit? Is a circuit on the polyhedra that goes through all the corner once without repeating, right? So that's without going back and repeating. That's the Hamiltonian circuit. And so as soon as this condition is satisfied, you can soften it. And we had a conjecture, and the conjecture is that you can always do it. 2 days ago, as I was preparing coming here, I received an email by this mathematician and saying, oh, you know, we enjoy your paper, and we've actually not only proved that your conjecture is correct, that every convex polyhedral tiling can be softened, but we also generalize it to locally polyhedral, where you can have a homeomorphism, you know, the kind of things that mathematicians like to do, generalizing. But essentially, now it seems that we have a theorem. I haven't gone to the detail, and it's still a preprint, but it looks very serious and very well made, so I can only assume that it's correct. So you can apply that to any form. For instance, if I take the truncated octahedron, I take the wireframe, I can now soften it, and the softened version of that is this shape here. It's very nice. That has 0 corners and at this nice curved shape. And if you print multiple of these, you realize that they satisfy the same condition. We'll talk again about these. They're quite nice. And you can do that for any kind of shape, and we've done that for plenty of shape. I'm not going to give you the detail, but you can also look around and you find interesting application of that, either in architecture, where you see some of this shape being used. And we had a project with friends of mine at the California College for the Arts in San Francisco, where they used that as a building block for biodesign. So these are actually made of ground eggshells with Bacillus subtilis bacteria as a mix in order to make these block and shapes, in order to create walls and things like that. But the nicest application that we found, which is found actually very deep in the ocean. So you probably have seen this picture of Nautilus, usually used as an iconic picture of what mathematics in nature is, you know, very observant and all that. For instance, it's on at least 20 different covers of mathematics textbook with always the same characteristics, is that none of these books ever talk about the picture or the animal, or most of the time it's mislabeled as being Fibonacci series, like in the Princeton Companion to Mathematics by Tim Gowers, where it's a logarithmic spiral, that's true, but it has nothing to do with Fibonacci. So these are shells, chambered shells. Nautilus is a cephalopod, it's not a gastropod. So that's why they have the gastropod do not have chambers, and the chambers that you see at this crescent shape, right? And so in 2D it looks like it's already in 2D. It looks like it could be a tiling, a way to tile with this different shape. But we're really interested in 3D, and 3D is fascinating because nobody has ever really looked at it until recently, when people started making CT scans of that, and a chamber of the Nautilus as this type of shape. So it looks like this. If you just look at a single one, it's quite remarkable. Now you extract it, and when you extract it, it looks like a shape like this. And then you look at the node where different edges come together, and you can again straighten it a little, essentially look like this shape in 3 dimensions. And this shape, now you can see that either you put a exponential scaling to make it bigger at each turn to fill space, or you can make it straight and you see that it fills space. It's very nice, natural structure that I built. So after we did this early work, we realized that there are other structures in science and in math that are very closely connected to the soft cell. And these are the triply periodic minimal surfaces. So let's go back to our friend, the soft octahedron. And so this is the truncated one, and this is the soft one, right? This one that I have here. And the way you can think of it, right away, you put a cage around and just look at the nodes. And the only difference that we do is we do this edge bending. We first change the edge and then we build the face. And so the difference is that the edge half tangent was like that, and now it's like that, right? And all the nodes are the same. It's very highly symmetric object. It's transitive. So you only look at one, and all you do, you change the half tangent so the two half tangent align. And the question is whether or not there are other objects of interest that you can create by changing slightly the rule and changing the half tangent. And if you go the other way, if you change the tangent the other way, you create a cell that looks like that. That's also a soft cell. It has no corners, just built of faces that are circle and then connected to them. And this cell is the unit self of the Schwarz P surface, the Schwarz primitive surface, which is a triply periodic minimal surface. So there are so many things to tell you about triply periodic minimal surfaces. I don't know if you had a chance to play with them. It's a wonderful world. So they divide space into two different regions, right? So if you're in the blue one or the yellow one, you don't mix. If you put vinegar in one and oil, you cannot make vinaigrettes whilst you shake it. There's no connection between the two. They are triply periodic, so one unit cell is periodic in the three direction, and they're minimal surfaces, so zero mean curvature, right? And Schwarz studied them as part of work in complex analysis and all that, and that's all this property. And that's the primitive one. And as I said, this has the structure between is very hard to understand, but the only one easy to do is for the primitive one. I'll show you in a second other ones. But so it divides space into region. That means if I make, for instance, cement block of these guys, and if I'm the first floor, I can only connect the third floor. So the complement of the surface that I show you is itself a Schwarz P surface. So they fit completely space if they were all made with block, right? So I can fill space with all these and having a double labyrinth of them. And so this is what I obtain by changing this angle. And now the question is, I left a space in between. What goes between the unit self of the P Schwarz and the truncated octahedron? Well, there is a other very nice type of structure that you find in physics by Lord Kelvin, which is the Kelvin cell. And Kelvin was trying to find a way, a unit cell that tiled the space, but that also respect the law of the form. And the law of the form is that you need to have equilibria at the different nodes, right? And so he reasoned you can have that if the angles are different in a truncated octahedron. You have 120, 120, and 90 for the square, and so that does not respect Plato's law at the node. And he said, and Kelvin says, no problem. I'm going to bend the edge a little bit. It's not soft, but it's a little softer than the usual. I'm going to bend the edge and bend the surface in order to have 109 and 109 and 109. And that tile space is the Kelvin cell. Not only that, the conjecture is that this is the one cell that has the minimal surface area for given volume in space. Still an open problem, all right? If you're interested to try to prove that. You can do a little bit better with two different polyhedra that also respect his law. That minimize that, but as a single monohedric shape, this one is supposed to be the best. And so now you have a complete view of these different structure that are now connected in this type of transformation, which is quite nice. But if you start with one triply periodic minimal surface, nothing stops you from playing the same game with different one. So for instance, the Schwarz D surface, that should be a D, not a P. The Schwarz D surface for diamond is the one on the right, and the gyroid is the one on the left. The gyroid was only found by Alan Schroon in 1970. He only died a couple of years ago. It's an absolutely fascinating surface. It's very mesmerizing because you try to make sense of what's inside and outside and all that. But these are the unit cell, and the unit cells are again soft cells. And not only that, they're not just mathematical curiosity. These pops up everywhere, right? Because the fact that they are minimal surface means that for fluid biomembrane, you can show that under the proper condition, it is a minimizer of like a Helfrich type energy. Right? But also you find them in plenty area of nature. A gyroid, for instance, is found a very good model for certain characteristic in the shape of the butterfly wings that gives you the glittering aspect of the wing of the butterfly because they act as photonic crystal. They have a phototic band gap due to the periodicity, and so they have these special optic properties. But as a material design, people also use them because they have optimal property for thermal exchange and other type of properties like that. So they're very well used in different type of microstructure in engineering for their beautiful properties. And now we know that we have different connection by changing different angles and group, and we have a new organization of these different type of surfaces. They also occurs in diblock copolymers, and they can be thought of as mesoatoms. So remember, diblock copolymers, it is a macromolecule, and they're composed of two distinct polymer chains, but they are covalently bound. So the polymer wants to separate, but the covalent bonds want to bring them apart. And the way they balance that struggle is by creating the structure of highly convoluted structure. And in the case where you have two different ones, they have two slightly different microstructure, and you can think of the different unit cells as different mesoatoms for these from which you can block. And so it's like a very complicated, funny shape a Lego brick system where the bricks are not square or rectangular, but they have angles, and you have to start playing together. So I want to finish by one nice application. I show you this picture on the first slide, and now you understand what it is. The wireframe is the wireframe of the soft truncated octahedron. The face of this one, which shows to be minimal surface. So how do you create it? You take the wireframe, you dip it in the foam, and the shape on there is by minimization of surface tension is a minimal surface. And that's the one that you see, the foam that you see on top of it. So you can create it like that. But what better place to have space-filling object than in space? So after we publish, we got a little bit of press, and people in Hungary were kind of interested in that. And Gabor managed to convince the Hungarian Space Agency to send one of these guys to the space station. And the idea is the following. If you take the wireframe now and inject water into it, if you just put enough water, the shape of the three-dimensional volume is going to be a minimal surface because you don't have gravitation, and so it's constrained by the boundary. And here is the movie of that. So you start with the frame, and all you do is, as they say, just add water. Okay, so you attach water, and it was a big success with people clapping at mission control, as you can see. So it's, according to them, it's the first minimal negative curvature surface made with water in space. And I don't know if it's really of any industrial use, but it does make astronauts really happy, you know. And you know, isn't that great? So that's how you can realize it. So let me conclude. So for the 2D case, we have a full classification. We start to organize to understand how this shape arise, and now we're going to see what the role this plays as an organizing principle for morphogenesis. In 3D cells, there are so many possibilities in 3Ds that you can only have partial classification. You can now start with any lattice and soften it, or you can start with a triply periodic minimal surface like the Schwarz P and do other things like this carbon allotrope, the Schwarzite, also composed of carbon, dibocopolymer, or you can do like the Weevil back, which is made of gyroids, and that's what also give the glistening. And so because we got a little bit of press, Scientific American got interested, and according to them, this was the coolest mathematical discovery of 2024. So let me tell you, this is for the bucket list, right? So you really want to have that. So thank you very much.
Thank you, Alain, for the coolest mathematical talk of the Albanova colloquium. Do we have any question? Yes, Dhruva.
So if you mix, say, lipid and water in different ratios, different lipids and so on, and then you get weird structures that I think some point called plumber's nightmares and things like that. These are all minimal surfaces of various kinds, right?
I don't know that, but yeah, I'd be interested in.
Okay.
You mean like colloidal assembly or things like that, or just lipids?
Just lipids, but these are.
Oh, you mean by hydrophilic,
by hydrophilic and
philic
hydrophobic
interaction?
Exactly.
Yeah.
So in certain ratios they form bilipid layers.
Yeah.
In certain ratios they form spheres.
Yeah.
But in other ratios they form these weird structures.
So Eureka, for instance, showed that some of the minimizer for this type of interaction lead to triply periodic minimal surface. That they are there. Yeah, correct.
Okay, Adrien.
So some of the minimal surfaces in 3D that you showed are very reminiscent of what we have in solid state physics, the Fermi surfaces of three-dimensional crystals. Would that be a way to generate a lot of these things? Because in principle you have the 230 space groups for 3D crystals, and then you would
I mean, that sounds very interesting, but I have no idea about this structure. But I certainly would like to know more. Yeah, as soon as you go to crystallography in 3D, or polyhedra, geometry in 3D of polyhedra or polytope, it's very, very difficult. There's so many different structures, so many groups, so many classification, that it's very hard to keep track. But mostly they're all on the hard side, on the polygonal side. So it's very interesting to see if there is a way to soften them, because in terms of physics, you realize that unless you have a crystal for which you have a regular structure and that's a minimizer, as soon as you go to more mesoscopic range, it's very costly to maintain any kind of corners, right? Because you need additional process to create corners because of surface tension and other effects. You would naturally soften things. So I think this language, this framework, is a natural way to capture that, to capture this.
Yeah, so Fermi surfaces are constant energy surfaces, but with the symmetry inherited from the crystal structure. So there might be some connection.
Okay, I put that in my notebook. Check Google for Fermi surfaces. Thank you.
Is there more questions? Andrei? Yes.
The problem is how to formulate question for a mathematician. Is there, let me say it, maybe it would be stupid. Is there any bijective correspondence between 2D and 3D geometry? Like, for example, given a three-dimensional soft tile and any plane intersecting it, would you always get a two-dimensional tile, which is also soft, or not? And what also happens in 4 dimensions?
So it gets very complicated. It is a very good question in geometry, the intersection with planes and all that. So we have one part of the one type of soft cell that we have, a prism, and prism are essentially 2 + 1 dimension because they all have teeth. You just pile them together, and then you go from 2 + 1 dimension. You automatically have the full thing. Now, the question that you ask is that if I start with something like that and take a plane in there, typically you would not get that soft structure at all, I think. It's a good question. So you get very strange things. For instance, you can start with a four-dimensional hypercube and take a cut, a projection of that, and you can generate, for instance, the Penrose tiling out of that. So you see that the periodicity of the four dimension is not carried at all with the same as the three-dimensional one. So these tend to be very difficult. It's very hard to imagine, but also very interesting. Some of the structure, like if you think a little bit more physically, some of the structure, like the one from the Nautilus, this chamber, you can think of them as being in a cylinder, and you have a balloon in a cylinder, and you take an arbitrary surface that cuts the cylinder, and the intersection of these will give you a shapes like the one I showed. So you can create prismatic three-dimensional soft cell by a section of a cylinder with a surface of given property. Yeah. It's another type of this structure.
Thank you.
More questions? Okay, I have one little. It's about morphogenesis, so in 2D. So have you looked at, like for instance, the pattern of some of the big cats, like the leopard, which has a structure a bit different from whatever you showed?
The spots and the...
Yes, that one.
So there's a huge amount of literature. That was one of the original motivation by James Murray with the mathematical biology to do reaction diffusion equation and understand pattern formation on the coat of leopard and all that. His original book, Math Biology, has actually a leopard with the stuff. So they don't fit so well in these because are they really tessellation or pattern that emerge? I mean, if they're just blob and all that by themselves, they automatically soft cell. If you count the white space and the black space as different cells, so there is not that much interaction between the two. So it's more a pattern that's generated without any real physics at the interface, if you want, between the two, unlike the cells and all that.
Yeah, so that was my question, basically. So this is not really a tiling, right?
Mm-hmm. Yeah. Okay.
But otherwise, if I think of the scales of lizard or snakes, then, I mean, these are soft cells, and as I observed for long ago. So why is the theory like so recent?
Well, of course, we haven't discovered them. They were all around. What we've done is finding commonality and finding a name for the type of structure and the right description, I think for that. Because in most type of physics or applied mathematics, typically you have a system and a type of pattern that you try to understand, and that gives to a large body of literature, for instance, originating from a partial differential equation, right? The whole work of Cross and Hohenberg, for instance, showing patterns appearing everywhere. But typically the recipe is always the same. You start with a system, you model it with certain PDE, and you see them arising as bifurcation of a steady state, or variation of that, or localized or not, and so on. Here we take the other approach. It says, we step back, remove the physics. What is the geometric commonality about this before we add any physics onto it? So I think it's a bit of a complementary perspective to the usual way that people think of pattern and pattern formation. Hopefully it'd be useful for something to think about this.
Okay, last question, Cristobal.
Thanks. The last question by Anthony makes me raise a question about the 2D tiling, the tiling of the plane. How does it get affected if your plane is curved? Like if you have an curvature?
Yeah, so I didn't talk about that, but of course the obvious generalization is to do an arbitrary manifold. And then you have a lot of interesting results. The results are known for the 2D-dimensional one. So people who haven't played with that, they probably have played with a football ball, right? And you see that the way you organize the pattern is quite different when you have a sphere than when you have a plane. And so in this case, the Euler characteristic is different, and you can add a term in the theorem that I show you that explicitly depend on the Euler characteristic. And that's why the number of corners in my example was less than 2, because you have to take into account the change. So that's well understood at that level. That's in 2D. In 3D, curve space, it gets very much more complicated. And so we don't really, we don't have yet results for that. But yeah, 2D, it's very well understood. It's very nice actually playing with the change in geometry.
Thank you very much.
Thank you.